Hello everyone, I am Shubhangi Agarwal and I would be presenting our work on position-aware GNNs, which was published in IJCAI 2021. Standard GNNs or graph neural networks rely on aggregating information from neighbors. Some of the well-known models are GCN, GraphSage, Graph Attention Networks, and so on. However, this ignores other underlying distributions and will incorrectly predict the same class for two nodes which otherwise have a similar neighborhood. For instance, in the figure on the right, vertices V1 and V8 belong to different classes, but have similar neighborhood structure. In such scenarios, the global position of the nodes with respect to the graph may be more helpful. The well-known deep walk and node-to-vec paradigms are useful in this regard, but are transactive in nature and cannot adapt to unseen nodes. PGNN is one of the first inductive graph neural networks to have captured the position of the nodes in the global context of the graph. The position is captured using shortest path distance of nodes with respect to select few anchor nodes, which are randomly chosen. The algorithm works fairly well but has its own pitfalls. Let us understand this with the help of this image. Here, let us assume that vertices V3 and V5 are selected as anchors by the algorithm, and we need to predict the labels of the vertices V1, V2, and V6. The shortest distance of all these vertices from the anchors is exactly the same as hence their embeddings would also be similar. This will enable the model to correctly predict same label for vertices V1 and V2, but will fail for the node V6. This encourages the need of an inductive position-aware graph neural network model which outputs node embeddings that retain maximum graph knowledge, incorporate semantics of the world, and are also resilient to small graph edits in an adversarial attack. We propose GraphReach as a viable solution. It has four components. In the first component, the graph knowledge of various paths is captured. In the second component, a diversified set of anchor nodes is selected through which the position of nodes is fixed. As part of the third component, node attributes and its position with respect to the anchors are combined for each anchor node pair. In the last component, the messages corresponding to each node are aggregated across the anchors. Let us see the workings of each of these components next. In the first component, to capture various paths and node positions, a set number of fixed length random walks are generated from each node. The visit count of each node in different random walks is then counted. For instance, let us assume a single walk of length 7 starting at V1, which visits vertices V4, V6, V5, V2, from where it revisits vertex V1 and V4, all in that order. The number of times each of nodes V1 and V4 were visited in this walk is 2. Similarly, V2 was visited only once, and thus the count for it is 1. For each pair of vertices Vi and Vj, we also compute a similarity measure, which is the average number of times vertex Vj is visited in all the walks originating at Vi, capturing position of vertex Vj with respect to Vi. In the anchor selection component, we try to ensure a diversified set of anchors in order to increase the reachability to distant nodes. For this, we sample a fixed number of walks from the previous step and create a bipartite graph to represent the reachability of the graph. K nodes are then selected such that minimum number of nodes from V1 cover maximum number of nodes from V2, which forms the anchor set. For instance, in the given bipartite graph, node 4 from set V1 is chosen as an anchor given its high reachability. After removing it from the anchor selection race, we remove the associated nodes and edges and search for another anchor. And in a similar way, we select node 1 from set V1 as another anchor. The process is continued till K anchors are found. We repeat this whole procedure multiple times to ensure a good anchor set. In the third component, the attribute of the node and the anchor, along with the distance between them, is combined into a message. Since our similarity metric is asymmetric, the distance of a node to and from the anchor is not same. We incorporate both these values in the message computation. Each node has a message matrix consisting of k message vectors, each corresponding to one of the k anchors. In the fourth and the final step, the message matrix is aggregated. For the intermediate layers, we apply a simple mean pooling of the message matrix and pass on the resulting vector as a node attribute for the next layer. At the output layer, for a position-aware embedding, we transform the message matrix into a k-length vector. This is the overall architecture of our proposed GNN. The model is initialized with the node attributes at the input layer. This is followed by message computation for each node using the pre-selected k anchors and mean pooling across them. The aggregated message is forwarded to the next hidden layer, while at the output layer, the message matrix is transformed into the output embedding. We evaluated our model on 8 publicly available datasets using 3 tasks: link prediction, predicting if an edge is present between 2 nodes; node classification, predicting the class of a node; and pairwise node classification, where we predict if 2 nodes belong to the same class. With GraphReach consistently outperforming state-of-the-art models, the table showcases the efficacy of the proposed approach in pairwise node classification. It reinforces that the approach is holistic and able to capture the position of the nodes. We also evaluated the models in the translative setting for comparison and noticed that traditional neural networks models work better in translative setting than on an unseen data. This could be because translative setting allows unique identification of nodes through one-hot vectors. We also tested attention-based aggregators, but the study suggested that mean pooling was just as good. Further, on studying the role played by node attributes on the embeddings, we observed GraphReach utilized the graph structural information better in absence of node features, while neighborhood aggregation-based neural network models seem to be exploiting the node attributes better. We also test GraphReach in an adversarial setting where we modify a small subset of nodes from the test graph and randomly connect them. Causing a significant perturbation with respect to all paths is difficult, with only a small number of graph edits, which makes the model more robust. This is also seen in the results with a negligible drop in accuracy of GraphReach in the adversarial setting. Upon visualizing the embeddings of different models, we can see that while embedding of traditional neural models do not show much pattern, the embeddings of GraphReach follow the pattern of the graph with nodes of the same community having similar embeddings. To summarize, we discussed the need of a graph neural network which is inductive, position-aware, retains graph knowledge of paths, and is resilient to adversarial attacks. The proposed GraphReach framework satisfies these objectives with significant performance improvement over state-of-the-art methods. The code and our paper can be accessed at the URLs displayed on this slide. Thank you.